Guys, this is my third video. Sorry for releasing it just one day before the physics exam. I was busy with my own revision too. So, anyway, the first topic is kinetic theory. Okay, yeah. So Uh, I'll be covering first the terminology, then the laws slash equations. Okay. Anyway, the first the terminology. So kinetic theory is all about uh, the movement of particles in a gas. So right, it's like you have this let's say gas chamber here, and inside you have like particles moving. You have particles moving uh, all around here, 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 some something like that. Okay, you get the rough idea. Okay, so basically it's just these particles, they're all moving around in random directions. Ran so it's basically like random Brownian motion. Move here, this could be moving here, this could be moving I don't know here. And they also can like collide and stuff. So yeah. Like they can collide and then the speed and the velocities and direction will change. So this can collide and make this one go faster, and yeah, basically that's it. So so there are three terms you need to know in kinetic theory. The first one is volume, which is the amount of space in the amount of space occupied by the gas. Okay, and the second term you need to know is the temperature, which is the average kinetic energy of uh, the particles of the gas. And lastly, the pressure is I'll say okay, the pressure is the amount of force exerted on the walls of the container um, um, when uh, the when the particles collide with it. Yeah. Well, you can just go and Google it to check. Google it to find out. But these should be the definition. The definitions. Okay, so now I'll be moving on to laws and equations. But before I move on to that, let me explain one symbol. This symbol. like yeah, something like this. So this symbol means directly proportional to. So what? So you probably learn directly. So I think you learn what you know what directly proportional to means. But I'll just explain to you for those who don't. So let's say you have y is directly proportional to x squared. That means that y equals k square y equals k square for some value k for some value k. So it's like for x like equal if x equals 1, 2, 3, or 4, y can be like corresponding values of y can be like 1, 4, 9, 16, or 2, 8, 18, 32, or any other numbers that are like you see, right? You there are like some value times all of this. Okay, so that's the symbol explained. So yeah. Okay, um so now I'll be explaining the three laws. So let me draw these two lines first. Okay, here and here. So the three laws are the pressure law. I mean wait, the first one is the Boyle's law. Okay, this order. Okay, and the second law is the pressure law. And the third law is the Charles law. Yeah, okay. So Boyle's law is basically PV is directly proportional to some constant value. Yeah. So that basically means right. If P okay. So that basically means if P increases by if you times the value of P by 2, then you must divide the value of V time by 2. Yeah. So basically it means P1V1 equals P2V P2V2, and yeah, basically means this P1 equals P2 V2. Okay. So for the pressure law, it means P is directly proportional to T. Like this. So if you put it in equation form, you have P1 P1 over T1 equals P2 over T2. Okay, like this. Okay. So lastly, the Charles law is the Charles law is the la you take the remaining two relations. So it's basically V is directly proportional to T. So in equation form, this means V1 over T1 equals V2 over T2. This. Okay. So, take note that um, take note that of a few things. So, first, so Boyle's law only applies when there's a constant temperature. Pressure law applies only when there's a constant volume. Yeah, and the Charles law only applies when there's a constant pressure. Okay. And also one more thing to take note is that the temperature is in Kelvin, not Celsius. Okay, yeah. So if you want to combine all the three laws, it's um, basically right. So it's basically like you can combine it like this. So okay. PV is proportional to directly proportional to T. And T1 P1V 1 over T1 equals P2V2 over T2. Okay, so actually, right, if you go online and search for this thing called the ideal gas law, it's basically like more complex version of this uh, a more complex version of this equation. Okay. Hmm. Okay, so I'll be moving on to the next part of the lesson, which is um, uh, uh, thermal properties. Okay, so um, our first, the first part is uh, the thermodynamics, and the second part is heat transfer processes. So this video I'll just be covering the first part, thermodynamics. So thermo so about thermodynamics. So first let us draw the heating curve of water. Hmm. Okay, just like this. Okay. Um. So is the this is the temperature in theta, measured in degrees Celsius, and this is the time in seconds. So let's say we are heating water, so the heating curve would look something like this. Uh, the first part is last part. Okay, yeah. So here's the heating curve of water, and uh, so here temperature is 0. Here the temperature is 100 degrees Celsius. So here we'll divide this we'll divide this graph into 5 regions. Okay, okay, so this is region A. This is region B, C, D, and E. Okay, so let's examine the 5 regions individually. So in A, the so it's basically just an A is the water is basically an ice cube that's gaining heat energy. Okay, something like this. So this is an ice cube, and in this region, it gains kinetic energy. So it's basically right. The particle the particles in the ice just move. They they just vibrate more vigorously as you raise the temperature. So for region B, it's basically the same ice cube. It's starting to melt. Hmm? Yeah, this is the ice cube, but it's starting to melt. Yeah, yeah, like this. So here the temperature doesn't change because the particles, the heat energy supplied is not converted to kinetic energy, but convert, but converted to potential energy. This is like the energy needed break break or overcome the bond. Okay, so here the particles do not gain kinetic energy, but the bonds between them are being overcome because of the heat energy. Like connect it, link it to your chem knowledge. In ice, hydrogen bonding is maximized compared to what in what liquid water. So here it's like basically overcoming some of the hydrogen bonds. Yeah. So in region C, basically we have a puddle of water. Okay. Yeah, something like this. So it's liquid water, and it's slowly, and as you as you continue to heat it, you will gain uh, Ke. The water molecules will gain Ke, and they'll move around more and more. So uh, in region D, you have the same puddle of water and starting to boil. This is the boiling point of water, right? So where is it? So here, like region B, the water molecules are gaining Pe as hydrogen bonds between them are completely overcome. So yeah, and in region E, you just basically have water vapor, water vapor, water vapor everywhere. Okay, so uh, so here once again the the water molecules are gain, gaining Ke, because as you continue to heat them, they'll just move faster and faster and faster and collide with each other more and more. Okay, so take note that I'm just using water as an example here. This doesn't need to be this, but this sort of heating curve applies to all other all other substances as well. Okay, like I don't know, sodium chloride or whatever substance. A few exceptions. So most of them, their graphs would look heating curve will look like this. In this will look like this, except for those that like Sublime or something. So anyway, let's continue. So here, so now I'll be explaining um, heat capacity and specific heat capacity. So hello. Okay, so let's say we have we have a water bottle here. Okay, and inside it has a certain amount of water. Okay, okay, just like this. Um, so first I'll be explaining heat capacity. So, is it? Alright, so let's just take the bottle itself, for instance. So, here, heat capacity is the heat capacity is the amount of heat energy you need heat energy you need to raise the temperature of a substance by 1 degree Celsius or degree Kelvin. So right, um, so the equation is Q equals um, C delta C delta T or theta. Okay, so delta, there's supposed to be a delta here. Uh, so right, let's say, so what do I mean? So let's say, just take this water bottle alone. Say the heat capacity is 50 joules per Kelvin. So what that means is that if let's say the temperature of this water bottle is 28 degrees Celsius right now, and I want to raise it to 29 degrees Celsius. So to do that, just the water bottle alone, all I need is to um, apply 50 joules of thermal energy, and the temperature of the bottle only would raise to 29 degrees Celsius. Okay, and let's say I want to raise it to 30 degrees Celsius, then I need 2 times of that energy. Okay, so here capital C is the heat capacity, Q is the thermal energy, and uh, T is the change in temperature. Okay, so now I'll explain specific heat capacity. So specific heat capacity, um, so it is the amount of heat energy needed to raise the temperature of a unit mass of a substance by 1 degree Celsius or Kelvin. So in a way you can say it is heat capacity of unit mass. Wait, uh, yeah, heat, heat, cap heat capacity per unit mass. Okay, so this unit mass can be either grams or kilograms or whatever. So the equation is Q equals mc delta T. Then I'll add the delta later. Here, m is the mass, C is the specific heat capacity. So what do I mean? So let's say this water bottle contains water, and specific heat capacity of water is 4200 joules per kg Kelvin, or 4.2 joules per grams Kelvin. So what this means is that say there's 500 grams of water inside uh, this water bottle right now, and, let's say it's at 28 degrees Celsius, like the bottle. So if I want to raise the temperature of the water inside this bottle to 29 degrees Celsius, then I need 500 times 44.2 joules of energy to raise this to raise the temperature of the water in the bottle to uh, 29 degrees Celsius. Or you can use 500 grams is also 0.5 kg, so you can multiply 0.5 by 4200 to get the amount of joules needed to raise the temperature to 29 degrees Celsius. And here, so you have this delta T, right? Delta T is, like here, it is the change in temperature. So if I want to raise it to 30 degrees, I just multiply by 2, 31 degrees multiplied by 3, and so on. Okay, so so say I want to raise the temperature of this whole thing, bottle and water combined, to 29 degrees Celsius. So let's put a note here. 0.5 times 4200 is 2100 joules, which is the amount of heat energy you need to raise the water here by 1 degree Celsius. So where is it? So wait. So total here, the total Q you need is equal equal to uh is equal to 50 joules to raise the raise the bottom to raise the bottle to 29 degrees Celsius, plus 2100 to raise the temperature of the water to 29 degrees Celsius, equals 4150 joule. So this is the amount of energy you need to raise the whole bottle and water combined to 29 degrees Celsius. If you want to raise it to a higher temperature, just multiply this by the temperature change. Okay. Okay, so I've added the terms and the equations here, and note that temperature can be written as either T or theta, a Greek letter here. So it can be, so for this equation, it can be like Q equals mc delta T, or Q equals mc delta theta. They both mean temperature. So one thing you need to take note is that this whole thing, only applies to region regions A, C, and E. Okay. Okay. So this whole thing and the equations Q equals C theta and Q equals MC delta theta. This only applies to regions A, C, and E because only in these regions there's a change in temperature. For B and D, you need something different called latent heat. Latent heat. So there are two types of latent heat. You have the latent heat of fusion uh, in represented by joules per kg or joules per gram, and um, you have latent heat of vaporization with using the represented using the same unit. Okay, and like this. So they are represented by L subscript F and L subscript V. So take note that it can be capital L or it can be small l. Okay. Okay. Erase this first. Okay, so I've finished erasing. So now I explain what is latent heat of fusion and vaporization. So yeah, um, so latent heat of fusion is the amount of thermal energy needed to completely melt a unit mass of a substance in the solid state. And latent heat of vaporization is somewhat similar, and I think I can tell uh you can kind of tell what it means. Amount of thermal energy needed to completely vaporize a unit mass of a substance in the liquid state. Okay, so for water, the LF of water is let me think. Is I think yeah, is about oh yeah, okay, so 3 okay, oh yeah, I remember now. So it's 3400000 joules per kilogram, or 340 joules per gram. And the L subscript B of water is 23000 joules per Kelvin kg, or 232230 joules per gram. So what this means is that basically, like, say you have 1 gram of water and you want to melt that completely, that 1 gram of water. So um, so that means that um, you have to so that basically means you need 340 joules of thermal energy to melt this 1 gram of ice. Oh wait, assuming you have 1 gram of ice, then you need 340 joules of thermal energy to melt this ice. For 1 kg, you need this much thermal energy, and for 1 gram of water to completely vaporize it, you need 2230 joules of thermal energy, and for 1 kg is this big number. And the equations are Q equals M times the latent heat of fusion, or the latent heat of vaporization. Yeah, okay, like this. Okay, yeah, so this, so to kind of where is it? So to kind of summarize it, it's basically, right, where is it? Okay, yeah. So basically, we regions A, C, and E, you can use Q equals C delta T, or Q equals MC delta T. Then for region for region for regions for region B, you need to use Q equals M L subscript F, and for region B, you need Q equals M L subscript V. What is the place to go? Yeah. Remove it here. Okay. Yeah. Wait. I think. Okay, so I've added in the symbols and stuff, and yeah, so basically, if you're this is the this is these are like when you need what equations you can use for what regions and things like that. Okay, so each substance has their own specific heat capacity and latent heat of fusion or vaporization. I'm just using water here as an example. For other substances like alcohol, these numbers could be different, and yeah, so uh for yeah so if you need, so for whatever capacity or specific heat capacity or whatever values you need in the exam, they will provide for you and you just use it. So here I'll end off my video. I'll end my video here and with very nice 4Qs here. And anyway, thank you for watching and bye bye. Very nice 4Qs here.